Okay, so in the first lecture, we were talking about what is marine biology and the fields of science that all work within the realm of marine biology, some of the different aspects, a little bit of the history, and just how marine biology got going and where we're at today, some of the technologies we're using today, and whether we talk about historical marine biology or current marine biology. In order to do this work in this field and study in this field, you have to use the scientific method. And not just marine biology, any field of science. Scientific method is essential. So everybody who is a scientist, even non-scientists, need to understand the basics behind the scientific method, how it works, how we set it up, and the knowledge we gain from it. It's not testing things like emotions, personal belief systems, things like that. It's testing natural, physical, tangible laws, things that, why is the water cold? Why does the fish have this structure, etc. So we take it from an objective perspective and look at running an experiment and designing it and gaining data, and it supports or rejects your idea. So when we're doing scientific method, we use reasoning. And there's two general types of reasoning or ways of thinking, inductive and deductive reasoning. Now, with inductive reasoning, you start with an observation and then you move forward to reach a conclusion. You're looking at something and saying, okay, I see this, I observe this, I'm going to figure out why it is what it is to reach a conclusion. And maybe your conclusion does not match your observation. Maybe it does. That's the nature of scientific method and the scientific process. With deductive reasoning, you have a statement about nature, something about a natural process, a natural scenario, and then you predict the results if the statement is not going to be true. So you're using kind of a different approach here to say, okay, here's this principle or this idea or this thing I'm seeing in nature, and if this is not true, then this is what it should be. And you design your experiment, you run your experiment, you collect your data to support or reject your statement with a deductive reasoning process. Now, years and years and years ago, it used to be an either or. People thought, well, it's either you're studying science with inductive or you're studying science with deductive. The reality is we use both types of reasoning when we're studying science. We want to look at it from a lot of different angles, and then when all of these approaches and these ideas all continue to support the concept you're trying to study, that's when we move into something pretty significant. We get into those things we call theories and laws. So let's take a look at the scientific method here. This should sound familiar. Hopefully everybody's had it before and you're just kind of reviewing this concept. If not, no problem. But just make sure you can do this. You're doing it on a daily basis. We just call it problem solving. Why won't my computer boot up? Why is my car not working? Why did I burn pizza when I made dinner the other night? Sorting that out and problem solving is the scientific method. So we always start with a hypothesis. So a hypothesis is a testable statement constructed from observations. So I burnt my pizza. There's an observation. Now what are you going to test? I burnt my pizza because the oven was too hot. All right, there's a hypothesis. It's a guess somewhat. So when we use the word hypothesis, we don't know the answer. We're not guaranteed to know the answer. We're making a guess. That's the nature of hypothesis. You then come up with your experimental design. So we need to test our hypothesis with an experiment. In good experimental design, you have multiple ways to test the same hypothesis. 4, 5, 6 different ways to test the exact same hypothesis. And when you're running an experimental design, the most important part of this, the critical essential key to this, is you want to control all of the variables in your experiment except for one. One variable is all you can test during an experiment. That way, you look at your results, you collect your data, look at your results. If they support or reject the hypothesis, you know it's based on that one variable, not 5 different variables. Then you say, well, which of the 5 is the one that caused this to happen? So always control the variables except for the one that you're trying to test. So you design your experiment, lay it out, list out all the materials, all the methods, be OCD on this. Make sure you have it to the minute detail. Collect your data. And you start drawing your conclusions from the data. Now, a lot of times you're going to need to go back and redo your experiment. Run it a second time. Run it a third time. Have somebody else run the same exact experiment. That's why having the details is so critical. Having the experimental design listed out step by step by step is so absolutely essential. Clear instructions. That way it can be repeated over and over and over again. It's basically you have a recipe. And if that recipe is not precise, what you get at the end changes every time. So you collect your data, and then based on the data you draw a conclusion, and the conclusion typically either supports or it rejects a hypothesis. So now you have an answer. If it rejects a hypothesis, okay, let me try a different experiment. Let me try another one, and another one, and another one. And if it keeps rejecting the hypothesis, okay, that's not sound. Eventually you may get to where you support the hypothesis. Test it over and over and over and over, and then you keep testing it, you keep supporting the hypothesis, you keep running different experiments. Now you have some solid information. Now you have answers to your questions. Okay, so in the field, we make observations all the time. You know, what's going on with these mussels, with the growth of the mussels in warm sites versus cold sites. There's our observation. Come up with a hypothesis. Is it the water quality that influences the growth? Is it the temperature? Is it the mussel type? Is it the food? You know, there's all these different experimental variables. So then you design your experiment, and in this scenario, you're going to do it in a controlled laboratory setting, so you can control all of the variables except for, in this example, the temperature. So you have to control the water quality to make sure both mussel groups have the same type of water, the same mussel type, no diseases, same type and amount of food, etc. You have to be that detailed and that precise to eliminate all those other variables except for temperature. And then you run your experiment, collect the data, and you might find out, you know what? Temperature didn't make a difference. Okay, that's not the variable that influences the growth. Let's shift and test a different variable. In this example, that variable did influence the growth rate. So think about the basics of scientific method. We're going to see a lot of things in the field. A lot of questions come up, and that's great. That's exciting, and that's the way science is done. But then you want to figure out, how can I answer that question? How can I test that question? That's the nature of science. So we collect all that data, we get all that information, we pull it together, and over time we reach the point of theory, scientific theory. Okay, this is something that's been tested over and over and over and over and not been disproven, not been shown to be false, not been shown to be wrong. Massive amounts of evidence to support it. That's when the scientific community says, all right, you got it figured out. This is a true statement. So you think about the theory of evolution, theory of plate tectonics, the germ theory, all these different theories in science. They've been tested, and we have not proven them false. It's not to say at some point in the future we can't or we won't disprove theory of gravity or plate tectonics or whatever, but right now, all those theories are solid. Okay, so that's a huge difference than when we hear the word theory in general. You're watching the news and they say, well, in theory, we think they should. They're still guessing. In science, theory is not a guess. Make sure you guys understand that as not just as scientists, but as anybody listening and watching and going through this material. When it's scientific, it's not a guess. You go to the doctor's office and the doctor's figuring out why you're sick. They're using the germ theory. It's not a guess. They're saying we know what causes disease and illness and we know how to cure it. We don't guess when we talk about theories. All right, so we got under our belts the basics of the science of marine biology. Our next lecture, we're going to talk a little bit about fundamentals of biology. Again, this is kind of overview for a lot of people. This probably, or hopefully, is a review of some of the basics of biology. And once we get through the next chapter with the review stuff, then we start diving into what are we going to see out there in the field? What organisms, what creatures are part of the marine ecosystem? All right, so let's sign off here, and then we'll check out some of the basic fundamentals of biology in the next lecture.